So, hi everyone, welcome to the AFMS seminar series again. It's great to have you all with us. Today it's my pleasure to introduce our speaker, which is Dr. Emilie Sauret, who is a professor at the Queensland University of Technology. Emilie received her PhD in turbulence modelling from the Pierre and Marie Curie University in 2004. She specialises in developing advanced computational models to understand complex fluid phenomena for a variety of engineering applications. So I think we're ready to take it away, Emilie. Thanks.
Thank you very much, Kat. Thanks for having me. I think that those seminar series are great opportunities to share our work among the Australian community. So I'm very pleased to have the opportunity to present what we're doing in my group. And so what I'm going to talk about this afternoon is the Lattice Boltzmann method and some developments for high order multi-component Lattice Boltzmann, and looking at some of the capabilities that we can achieve, especially for non-ideal fluid flows and mixtures. So before going into the details of the presentation, I'd like to acknowledge part of my team. In particular, Chris Fromm, who's now moved as a postdoc at the University of Manchester, Zonzang and Vedad, who are working with me at QUT. I would also like to acknowledge the Australian government, Australian Research Council, for the funding that they're providing to me. So let's start with a bit of a motivation in terms of the work that we are carrying out in the group. And so basically what I have here is a couple of examples, and that would lead to some questions of the commonalities that those applications may have, whilst they may seem very different. So I'm starting with some cup of coffees, depending on who you are and what you like, from the black coffee here to something that is very diluted with milk there. I've got some lab-on-a chip applications for microfluidics, biological assays, disease diagnostics, for example, etc. On the bottom left, I've got some 3D printing. Doesn't matter if it's melt electrowriting, melt electrospinning, different technologies of 3D printing for different applications. And then on the right-hand side at the bottom, we've got some organic Rankine cycles that are used to recover waste heat from medium to low heat resources. And so basically the question is, what do those applications have in common? Because as I said at the beginning, they may look very different in terms of the applications type. So actually, they've got lots of commonalities. They're all dealing with complex and non-ideal fluid flow and mixtures, where basically we have very strong inter and intramolecular interactions. And through those strong interactions, we obtain fluids that are no longer in equilibrium, and so we've got this out of equilibrium phenomena that we need to take into consideration. We also have complex fluids, for example, for 3D printing, due to the nonlinearity and statistical fluctuations that occur in those fluids, especially when we look at viscoelastic fluids, and that lead to non-ideal instabilities that are, again, quite complex to physically understand, comprehend, but also numerically and computationally model. And on the right-hand side, these organic Rankine cycles often are trying to use some mixtures of these organic compounds to provide a much higher degree of freedom to optimize those applications so that we can extract basically more energy from a given heat source. So despite those broad areas that I've just presented here, there's lots of commonalities in terms of the complex fluids of those mixtures and non-ideal fluid flows that I'm interested in. The common challenges for those applications includes the lack of fundamental understanding of those fluid flows because of the complex behavior, the complex flow dynamics of those fluid flows and mixtures, in particular when we consider those out of equilibrium phenomena and instabilities. We also lack accurate and fast computational tools and models, in particular for practical applications. And because of those two, basically we are lacking proper engineered design and optimization methodology, and that obviously limit the development of novel microfluidic applications, but also energy efficient renewable technologies. And that's actually the two areas that I'm interested in, microfluidic on one side and renewable technologies on the other side. So linking those two with some common challenges that can be worked on, basically. So now that we've got this background in terms of what we are doing here and what we are looking at, what I want to look at now is the motivation for the Lattice Boltzmann approach. So in here, I'm looking at different scales, the length and time scales. And so what we are looking at is, first of all, what happens at the micro scale. So what happens is in your cup of coffee, for example, when you're mixing your coffee with milk, and looking at really those molecular interaction at the micro scale. And from there, moving on to what happens at the macro scale. How can we get into the continuum limit and look at massive, large application? In that case, we are looking at Kelvin-Helmholtz instability that we observed actually in Brisbane sky. And so those instabilities, how do they relate to the macroscopic molecular interaction that happens at the micro scale? And so the question is really, how can we link those two worlds together? And so, of course, at the macro scale, we've got some descriptions. We've got the continuum picture with our macroscopic quantities that is governed by the Navier-Stokes equation. So that's something that is well defined and well known. At the micro scale, we also have some microscopic description. We can track individual molecules. We can develop some particle-based solvers that are usually governed by Newton's dynamics. So that's fine. But again, the question is, how do we relate those interactions at the micro scales that will impact on the dynamics at the macro scale? And so to do that, one way is to use what we call mesoscopic descriptions, and in particular using the Lattice Boltzmann approach, which is going to look at a representative collections of molecules, so not only tracking each individual one, but a group of molecules, and that's basically governing by the kinetic theory. So we now have kind of a bridge here that can link the microscale to the macro scale. And so really the idea of using Lattice Boltzmann is to provide the balance that we need between the individuality of the molecular details that are going to be expensive to computationally model, and at the same time providing the universality of conserving our Navier-Stokes equation, so the conservation of flows to get our macroscopic quantities. And so the Lattice Boltzmann is a good way to balance those two together, and that also opens some opportunities to look at applications where we've got coexistence of physical, chemical, and biological phenomena at those mesoscopic scales, basically. Now, in addition to that, as mentioned, if we look at the microscopic approach, they can be very computationally expensive. However, we know that we are improving the computational efficiencies of our platforms, of our computers. We've got better architectures, better materials. We've got surely a clear increase of the computational performance that we can reach. And so again, using the capabilities of the Lattice Boltzmann for parallel computing and scalability is another big advantage that we can exploit to look at these applications where we have lots of different phenomena, physical, chemical, and biological phenomena that coexist together. An example here is looking at cellular hemodynamics. So for example, looking at red blood cell simulations in large coronary trees, for example. And so the requirements in terms of computation will be huge. But again, with the increase of computational capabilities and the capabilities of Lattice Boltzmann, then that's probably something that we could achieve in the future. So moving on from here, just think that I forgot a slide, not weird. Anyway, so now what I want to discuss is, now that we have the motivation for the Lattice Boltzmann to link the microscale to the macroscale and have looked at the potential for Lattice Boltzmann, what I want to cover is the use of higher order Lattice Boltzmann. So I'm going to start with the Lattice Boltzmann method in general. And so, as I said, what we are going to look at is a bunch of particles moving randomly in a domain. And we are going to create a distribution function that's going to represent the motion of those particles, and that indicates the density of the particles at a specific position. And we are going to associate this with different discrete velocity that you can see here at a specific time. So we are going to define this distribution function with some statistical probability, and we are going to assign some weights to those discrete direction. Now, when we do the summation of those weights here, represented here with the different discrete velocity, and basically those discrete velocities are the velocities at which in which the particles can move, then this is going to be equals to the speed of sound squared. So the speed of sound of the actual lattice. And so what we have is, then we can define an evolution function. So that's involved the initial distribution function of those molecules. We've got a collision term, and then we've got the streaming term, which basically tells us that those particles are going to collide at a specific node or location on the lattice. And depending on the collision, then they are going to have a different velocities that they will move back along the direction of the discrete velocities. And so they are going to move to another position in the lattice structure. And then if we've got any additional external force, then we can account for that with this equilibrium forcing term. Now, in the collision, we've got also an equilibrium function that we need to define. And I'll talk to that just after that. So now the question is, that's the overall idea of the Lattice Boltzmann approach, but the question is more about why do we need to move toward a high order Lattice Boltzmann? So basically, the lattice structure that I've shown you with 9 different discrete velocity is the most basic lattice structure that we can have. The problem with this structure is that it's not enough to recover the full Navier-Stokes equations, and I'm going to show you that later on. So if we want to be able, and again, that links back to the fact that we want to link the microscopic, the molecular interaction with the macroscopic variables that we want to obtain. And so to be able to recover the full Navier-Stokes equations, we can use higher lattice structure. For example, this D2Q17. This one will have a higher order of accuracy. So this one is going to be a 3rd order accuracy, while the D2Q9 is only a 2nd order accurate. That's good, that's getting better, because with this structure, we can recover the full non-thermal Navier-Stokes equations. But again, it's not enough to fully recover the thermal Navier-Stokes equations. And if we want to be able to recover those equations, then we need to move to a D2Q49, which has a 4th order accuracy. And so what do I mean by order of accuracy is basically linked to this equilibrium function that I mentioned before in the evolution equation. So this equilibrium function is obtained by expanding the Maxwell equations by orders of Hermite polynomials. And once we've done the expansion, we can expand to the 1st, 2nd, 3rd, 4th order as much as you'd like. And then we project these truncation terms onto a Gauss quadrature. That's the lattice structure of the Lattice Boltzmann method. in here, what we have, so the first and second order, that's the standard lattice Boltzmann, that the D2Q9 that I mentioned before. This expansion, unfortunately, doesn't satisfy the Galilean invariance because of the scaling error that has a third order term. And because of that, as you'll see, we can't recover all the moments that we need to recover the Navier-Stokes equations. If we add the third order and fourth order, so if we move into the high order lattice Boltzmann models, then we've got greater isotropy and we can actually recover higher order moments. So what does that mean to recover higher order moments? Basically, the physical quantities that can be retrieved from the distribution function is presented here. So we've got the zeroth order moment, which is basically the density that can be obtained with the standard lattice Boltzmann. And we can also recover the first order moment, which is the momentum here. However, we are limited to those two because of the order of accuracy of the standard lattice Boltzmann. If we move to the higher order lattice Boltzmann, then we can see that we can recover the second order and the third order moments, which are the pressure tensor and the heat flux. And that's how we can fully recover the full thermal Navier-Stokes equations. We need those two moments to be able to retrieve the Navier-Stokes equations. Again, meaning that we need this high order lattice Boltzmann. So just to summarize, why high order lattice Boltzmann? Because it's Galilean invariant, so we can recover the correct momentum dynamics. We can recover the full thermal Navier-Stokes equations, but we can also go beyond those fluid flows. We can also go beyond the Navier-Stokes level at Knudsen number converging to 1. So we can also describe slip and transitional flows. We can also minimize spurious velocities because we can recover higher order isotropic gradients. And again, we still have the same scalability and parallel capabilities that I mentioned before to hopefully speed up the simulations. So with this high order lattice Boltzmann, what we've done is doing some investigation into the accuracy and the stability of those high order models. So in that case, we looked at 5 different lattice structures, the Q9, Q17, Q25, and Q49. So for each of those lattice structures, we've got different order of accuracy. This is this N term here, from second order accurate for the Q9 to a fourth order accurate for the Q37 and Q49. This accuracy then linked to the level of rotational isotropy from 4 to 8, and the higher the isotropy, basically the more accurate that is. Then we've got the characteristic scales of those models represented here through the speed of sound of the lattice structure. And so what we've done on top of this Q49, we've rescaled this Q49 lattice structures into 2 different structures, the Q49 star and the Q49 cross, just to make sure that we can also compare those models at the same characteristic scale. So we now have the Q49 stars, which has the same speed of sound as the Q17 and Q25, and the Q49 cross, which has the same speed of sound as the Q37. So we can compare them too. We looked at first the accuracy on the Taylor-Green vortex. So we've got 4 quadrants with contra-rotating vortices in here. And we've got an analytical solution that we used to define the error between the calculations for each lattice structures and the analytical solution that we have here. And so what we have on the right-hand side is the comparison for the error. And what we can see is that when we move towards higher order discrete velocities term lattice structures, then we've got a reduction of the error compared to the standard lattice Boltzmann. So basically the accuracy is improving, and it's almost a 2 order of magnitude increase of accuracy between the Q9 and the Q17 and Q49, basically. In terms of stability, we've used the double shear layer as a classical benchmark case to test stability. And so we define two longitudinal shear layers at different location, y, so one on top of each other. And then we define a transverse perturbation along the y direction here that is creating some perturbation that will lead to the shear layer roll-up and generate those two counter-rotating vortices that you have here. So on these videos, I've got the Q9, so the standard lattice structures, and I've got two grid resolution, a low resolution and a higher resolution. And what we can see is those additional secondary vortices that appear with the 128 grid resolution. And that's an indication of some instabilities that occur. So if you look at these extra additional vortices here, that's an indication of an unstable simulation. When we increase the resolution, we don't have those secondary vortices. So we move into a stable simulation at a higher grid resolution, basically. And so what we did is we compared again the Q17, Q25, and Q49 on this benchmark case for two different grid resolutions. And what we can see is that for the Q17, we've got those secondary vortices that appear. They tend to decrease in size as we increase the grid resolution. However, what we can see that for the higher velocity term models, Q25 and Q49, we don't have those vortices, those secondary vortices anymore at all with the refined grid. Even with the lower grid resolution, those small instabilities are quite limited compared to what we have with the Q17, for example, or the Q9. If we look at now, if we move into a stability analysis for those models, what we've done is running the simulation of a range of Reynolds number, and we determine the maximum Mach number achievable to stay in a stable region. And so what we have is here the maximum Mach number on the vertical axis along with the Reynolds number. And what we can clearly see that the red one at the bottom is the Q9, so that's the standard Lattice Boltzmann, which basically has the lower stability range. Now, if we also compare the Q9 versus the Q17 and 25, so this yellowish and grayish ones, and versus the Q49 and Q37 at the top, we can clearly see that we are increasing the stability as we increase the number of discrete velocities in our lattice structures. Now, we can also see some small difference between the Q17 and the Q25, so these two, especially at higher Reynolds number, but remember that those two have the same characteristic scale, same isotropy, and same expansion order. So they should be exactly the same. The only difference is the number of discrete velocities. And we've got the same comment when we compare the Q37 with the Q49 cross, okay? Where at low Reynolds number, there are some slight difference, that's too major, but at higher Reynolds number, we've got this big difference between this Q49 that has been rescaled and the Q37. And so really there's a strong connection between stability and the number of discrete velocity in our lattice structures. That's not the only point that we have from here. We also see some stability dependency on the reference temperature. The reference temperature is basically equals to the squared of the speed of sound, okay? And so if we compare the Q49 and the Q49 star here, the green one, okay? We can clearly see a drop of stability. Remembering that, again, they've got the same, those three Q49 have the same number of discrete velocities. The only thing that is changed between those three is the characteristic scales, okay? So there's, again, a link between the reference temperature through the speed of sound and the stability of those lattice structures. So the problem is becoming then quite complex and difficult to apprehend. But to summarize this accuracy and stability analysis, we use the double shear layer and the Taylor grain vortexes. We show that the accuracy is increased as we use higher term lattice structures, and we see some stability improvement also when we are using those higher term lattice structures. However, there are still some differences between some of those structures, especially when we look at the Q49 and the rescale Q49s, where we have shown some stability dependency on the reference temperature. There's surely some more investigation into stability of those high order lattice Boltzmann structures that have to be carried out further, basically from this investigation. So now that we know why we need a high order, now that we know that those high order structures or lattice Boltzmann method give us good accuracy or better accuracy and stability than the standard lattice Boltzmann, what I want to move on to is using those higher lattice Boltzmann to develop a multi-component lattice Boltzmann method. Because remember, what we want to investigate is non-ideal fluid flows and mixtures. So we need a multi-component model. So to do that, to include those non-ideal interactions at the molecular level, what we are using is the Shen-Chen pseudopotential that is helping us mimicking the molecular interactions through this term, the force interaction term. In this expression, we've got the self interaction, the cross interaction, and the fluid structure interaction between the different components of the mixtures and the wall, so W for wall. Now, what we need is to relate the transport properties at the macro scale through these two parameters, so the pseudopotential and G, which is the interaction strength, and that's going to help us controlling the force or the amplitude of the interactions in different cases and scenarios that we are looking at. So also remember that going back to the fact that we want to link those interactions at the molecular level with the macroscopic fluid equations and the macroscopic variables that we want. So we can have this link using the Chapman-Enskog analysis. However, to do that, we need to have the interaction pressure tensor. The problem with this interaction pressure tensor is that it's going to depend on the competing interaction that we have in those non-ideal fluids and mixtures. This interaction pressure tensor is also required to describe the dynamics of the fluids at the fluid interface when we've got two fluids. So for pressure, surface tension, diffusion, but it's also important not only for multi-phase flows, but also for multi-component flows where we've got those interaction. So when we look at the total momentum flux tensor, that is going to be needed to link the microscopic scale with the macroscopic parameters. We've got two terms here. We've got the kinetic part, and when the fluids and flows are near equilibrium, we can definitely obtain a relationship with that is defined here to obtain this kinetic part of the expression. But on the other side, we've got this interaction pressure tensor that we need to figure out. For this tensor, we've got two different approaches available. We've got a differential approach on the left-hand side, and we've got the exact lattice theory on the right-hand side. The differential approach is the divergence of the pressure, which is going to be equal to the force that has been defined before using the Shen-Chen pseudopotential. So we've got this right-hand side term. From here, we can, or it has been established in the literature, that we can have a continuum relationship for this standard pressure tensor component. That's the general solution. However, with this approach, the problem is that we do not have a discrete solution for the pressure tensor. So everything goes back into the continuum limit, and we don't have the discrete solution. On the other side, the exact lattice theory is going to give us the exact discrete formulation for the pressure tensor. The problem is moving from the discrete pressure tensor to the continuum limits. Again, the literature has shown that we have some solution at the continuum limits, but those solutions are lattice dependent. So it's going to be dependent on the lattice structure that we are using. And at this stage, basically, there was no solution for high order lattice structure. So we had the solution, the continuum limit pressure tensor solution for the Q9 or for 8, so a isotropy of 8 lattice structure that we have, but we don't have anything for high order lattice structures. And so we are missing different things on both those approach. On one side, we don't have the discrete lattice level information. And if we don't have, we can't get the continuum level. On the other side, we've got the discrete solution and we can retrieve the continuum level, but there's no generalized solution for that, meaning that we can't have a generalization of our macroscopic properties such as diffusion, surface tension, contact angle, and pressure. So the question that we had from there for us was how to establish a general expression for the interaction pressure tensor for high order lattices that is complying with the discrete definition and include all the interaction that we need. And then how do we find the continuum approximation from this discrete solution so that we can retrieve the macroscopic variables? I'm not going to go into the details of how we are going to get this very long expression, but basically starting back from the exact lattice theory here on the left-hand side, we have been able to retrieve this expression for the interaction pressure tensor at the discrete level, okay? Using this expression and using Taylor expansion, we have been able to demonstrate that we can retrieve the continuum approximation for the pressure tensor. And this is just an example for 2D example for the normal component of the pressure tensor. Now, the big advantage of those two expressions is that they are valid for any lattice structures. So no matter which lattice structure that we are using, we can use those expressions basically. And that's a big advantage because then we can move from the microscopic to the macroscopic variables using a high order multi-component models. From there, what we did is making sure that the solution was correct and that we validated the solution that we've obtained. We looked at a flat interface where we've got the white region, that's one component on both sides, and another component, the black one here. And we looked at the middle line here. We looked at the pressure on this line, which has to remain constant through. And then we've got the variation of density because of the two different components that we have. That's the gray line here. And so we've got the continuum solution for the standard solution that we have in purplish. And we've got our continuum approximation that we derived from our exact discrete solution. What we can see is that both those two, the discrete and the continuum limit solutions, respect perfectly the constant pressure on this line, while the standard solution surely has some inaccuracy at the interface. We've got this spike here occurring. Moving from there, what we looked at is the mechanical equilibrium conditions. That is basically the gradients of the pressure that has to be 0 because, as I said, the pressure should be equal, should be constant through the interface. And so we tested different lattice with different higher order isotropy structures. And what we can see is that the high order isotropy structures maintain perfectly a constant, a 0 value of this gradient of the pressure, which is exactly what we wanted to have. There's a slight variation for the Q9 lattice structure, but when we look at the scale here, it's basically the machine accuracy. It's 10 to the power negative 15. So it's completely negligible. So we clearly have the mechanical equilibrium condition that is satisfied, and we demonstrated that is satisfied for any lattice structures, basically, which is good. And then we moved on to different validations. We moved from there on to the Laplace experiment. Now that we have and can retrieve the pressure tensor, we can have the normal and tangential pressure component for the Laplace experiment. And with that, we can calculate the continuum surface tension, sigma. And with that, we can calculate the Laplace pressure. And again, we compare this Laplace pressure against theoretical approximation for different lattice structures, moving on to our high order Lattice Boltzmann approach, and all those cases match pretty well with the theoretical approximations. Then once we've got this surface tension, then we can keep going and define the contact angle using the Young's equation here. And so what we can do is we can look at different scenarios of different conditions for neutral, hydrophobic, or hydrophilic surfaces. And we've got the red solution, which is extracted from our high order multi-component lattice Boltzmann. For the neutral case, we actually obtain exactly 90 degrees, which is what is expected. And when we compare against a droplet shape analysis tool and the geometrical approximation given here, we can see that there are some slight differences and they are not as good as our Lattice Boltzmann approach. When we move on to the hydrophobic case, again, we match pretty well with the range that is provided with those other approximation for the contact angle. And similarly for the hydrophobic case, we also match pretty well with the droplet shape analysis tool that we compare against. The difference with the geometrical approximation, we are thinking that it's mainly due to the geometric resolution in terms of estimating this L and H parameters of the bubble size. And now from here, now we can move on to using all the previous information, especially the pressure tensor, using our Chapman-Enskog analysis to obtain the full general advection diffusion equation at the continuum limit. So that's this big equation. The main point here is to see that the term under here is the diffusion coefficient, okay? Which means we can retrieve this diffusion parameter. And we can retrieve this for different cases. In case it's a miscible or immiscible mixture, we would have two different parameters, C, that is linked back to the critical limit. So when the diffusion is equal to 0, that can be defined. And so we can approximate both miscible and immiscible mixtures and diffusion in those two different cases. So here, what we've done to check if that was working well, we looked at a miscible test case where we've got a sinusoidal decay of a binary mixture, considering both the inter and intra molecular interactions, and looking at the diffusion coefficient for different lattice structures and comparing against, again, the theory that is provided here. And again, our simulations for all those high order lattice structures match pretty well with the theory. So we're pretty confident that it's all working fine. And then we move on to some preliminary investigation of what it could look like to have miscible and immiscible mixtures using those high order multi-component lattice Boltzmann. So we looked at a near miscible case where the fluids can partially mix. And so if I play the video, we've got two different components on the left and on the right. And so what we can see that they're mixing almost completely, but not completely, because again, we're at the miscible limit. when we move into an immiscible mixture, we can run the same simulation. And again, that was just preliminary investigation or, you know, interest to look at what's happening and if it's behaving as we were expecting the solver to behave. And in the immiscible mixture, we can clearly see that those two components are separating from each other and are clearly separated instead of the previous case. So again, giving us confidence that that everything is working as it should. Then we also tried, and that was more a trial to test the capabilities of those high order multi-components Lattice Boltzmann method for ternary mixtures. So looking at different concentration of 3 different components and looking at different cases. The left-hand side is a glass-like morphology type of ternary mixtures. And on the right-hand side, we've got something that looks like more a bubble morphology. We can clearly see some bubbles forming among those different fluids. So again, we can really look at a variety of mixtures using those Lattice Boltzmann models. The last point that we were looking at was a demonstration of the capabilities of our developments around those high order multi-component Lattice Boltzmann to really investigate both the fact that we can look at miscible and immiscible mixtures using the diffusion coefficient that we can establish from the pressure tensor, and looking at also realistic mixtures. So in that case, we are looking at zeotropic mixtures where the boiling points of the 2 components are different. And in that case, I look at 2 components, R134A and R245FA, which are very common organic fluids in organic Rankine cycles for renewable energy applications. And so what we've done is we compared the simulations at the critical points here against some theoretical predictions, looking at obtained with the Maxwell constructions. And again, we are matching pretty well those points here. And then what we've done is looking at the both miscible and immiscible cases, where we've got, in that case, we've got 2 components, A and B, so those 2 organic fluids. But on top of that, we also have 2 different phases, liquid and gas, so white and black, white and black. So basically, we've got multi-phase, multi-component simulation in that case. And we've got the miscible and immiscible comparison here. And again, that was purely a first trial or attempt to see how we could use those high order multi-component Lattice Boltzmann for more complex non-ideal mixtures. Again, it seems to work pretty well, but there are surely much more work to carry on that topic. And then now that we have that, just briefly, I just wanted to show some of the qualitative assessment that we've done for non-ideal instabilities. And basically what we looked at is Rayleigh-Taylor instability. We compared, again, different lattice structures, so the Q17 with the Q49 cross. What we can see is that the general behavior is pretty similar. And when we look at the entropy and velocity streamlines, again, the comparison between the Q17 and Q49 is very consistent, okay, which is very good because that's exactly what we wanted to achieve. So really having a high order multi-component Lattice Boltzmann that is providing us consistent results across all the lattice structure that we can use. And finally, I've got the Kelvin-Helmholtz instability. That's just a qualitative visualization of it. But again, when we compare the Q17 and the Q49, having the transport properties that we are now able to obtain from our high order multi-component Lattice Boltzmann, then we do achieve really good consistency between those structures. So when we compare at different times, those plots, they're pretty similar. Okay, we haven't been further in terms of doing some more quantitative investigation between those lattice structures for those instabilities, and that's, you know, that would be probably future work at some stage. But that's where we're up to in terms of the developments of the methods at this stage. So to conclude and to give you a bit of perspective on that particular work, so what we've achieved is a general solution for the interaction pressure tensor for high order lattices. And we have obtained a continuum approximation that we have validated on different cases. That allows us to have all the macroscopic variables. Equation of state, I haven't shown that, but we have the equation of state that we can retrieve, the diffusion, interface tension, contact angle that we have validated, and that's what I've shown. We've got preliminary results for instabilities. The most important in those preliminary results is the consistency between the lattice structures, between the Q17, 25, 37, 49 that we obtain for those non-ideal fluid flows and mixtures. So we now have a high order multi-component lattice Boltzmann that can be used for those non-ideal fluid mixture, which is a big step. Now from there are still many things to do. As I mentioned along the way, we can work on investigating a bit more the stability and robustness of those high order lattice Boltzmann methods. But there are also some work to do around the realistic boundary conditions, in particular for practical applications. In all the examples that I've shown you, basically we are using periodic boundary conditions. So having more realistic boundary conditions would be a step further to apply those models for practical applications. Another interest of us is to combine those models with our red blood cell membrane model, which is allowing us to model any red blood cell morphologies from stomatocytes to discocyte to echinocyte, and so that we could couple that to look at the flow of those morphologies in circulation, basically, and having a fluid structure interaction between this model and the fluid flow. The other thing that we are really interested in is coupling this model with a viscoelastic model to extend the applicability of the model in particular. So one is cellular hemodynamics linked with the red blood cell membrane model that we have, but also looking at mixings of viscoelastic fluids for microfluidics. So that's something that would be very useful in microfluidic applications. The other aspect that we are looking at is moving into elastic turbulence, which is a very interesting regime where we are operating without inertia, basically. We are working with very low Reynolds number. However, we've got nonlinearities that are triggering elastic instabilities. And so we've got a coupling between viscous and elastic stresses that can occur, and that's what you can see on the video here of a 4-roll mill benchmark case where we are stretching some polymers, and after a while we've got a complete chaotic regime that is obtained, and we've got those quadrants of vorticity that is basically turning around the 4 quadrants of the domain. But it's really chaotic regime, and that's why it's called turbulence, because it has some similarities with the inertial turbulence that we know, but again, that is in absence of inertia at very low Reynolds number. So it's mainly driven by viscous and elastic stresses of viscoelastic fluid flows. So again, those applications are, can be very important for mixing in microfluidics, where mixing is a difficult process to achieve. And so that's using those high order lattice Boltzmann approach coupled with viscoelastic models would be a great addition to the tools that are currently available, basically. And I think that's all for me. Thanks a lot for listening, and I'm happy to answer any questions that you may have.
Fantastic. So thank you so much for that talk, Emilie. That was fantastic hearing about the high order Lattice Boltzmann methods. We do have some time for questions. So if you're in the audience and you have a question, feel free to, oh, we've already got someone in the chat. But everyone else, you can either put your hand up or you can just unmute yourself and go ahead and ask. So we might start with the question in the chat. I can read it out, or would you like to read it, Emilie?
Yep, no, I'm happy to do so. Curious with the high order lattices you are discussing, are these not termed multi-speed lattices in the Lattice Boltzmann literature, as the lattice discretization doesn't necessarily mean the scheme will have high order convergence, or are the methods you are using different from the multi-speed methods in the literature? So basically what I've been naming high order is, if I maybe move back, that's a bit slow, I've got too many slides. If I move back, give me a sec. Whoops. Okay, so moving back here, what I'm calling high order in this case is really about the order of expansion that we are using for the equilibrium function. Okay, so how many order of expansion are we having in the equilibrium function here? Okay, so moving to the third and fourth order is the high order terminology that we are using. Okay, now once we've got this expansion, okay, we still need to do the projection on the lattice structure, which is depending on the number of discrete velocities that we are going to have. Okay, so we can then project those onto our high or multi-speed lattices, if you want to call that like that. Okay, and so we can mix and match. We can, you know, use a second order standard lattice Boltzmann, but then do the projection on more discrete velocities, and so we could achieve a higher isotropy, basically. Okay, so we can mix and match those. Okay, so that really depends on the terminology that you want to use. For us, the high order is really the expansion that we are using in the equilibrium function. Hope that makes sense.
Great. So thank you for answering that, Emilie. Any other questions coming from the audience? While we wait for people to gather their thoughts, this is quite a basic question, but when you do go to a higher order, or even changing the lattices, I guess is the question. So going from like Q9 to Q49, how much more computationally expensive is that? Or is it because you have to go to a high resolution grid?
Yeah, so it's linked together. Okay, so what we have seen, however, is that moving to the Q49 will surely increase the computational cost. Okay, that's no question about that. However, what we've also seen is that the accuracy and stability would be better, and as such, we don't necessarily need to use such a high grid resolution either. So we can try to balance a bit, okay? But that's still very much expensive, okay? And so that's still something it's under investigation, because again, that's not, you know, a Q49 is probably not the solution for practical applications, okay? Unless we move to GPU. So the other part would be to move into GPU to really accelerate the processes that we have. There are always some more, you know, computing strategies that we can use to speed up the simulations.
Great, thanks. That answers my question. Anyone else in the audience? Yep, we have a hand up. Go, take it away.
Yes, thank you for this presentation. I like it. And the thing that I was thinking, you talk about that Q49 can do thermal flow. imagine that you have a multi-component thermal flow. For example, the practical thing is that when we inject supercritical CO2 in the pore structure, which is fully saturated with the salty water, it's first evaporate the water. I was thinking that, is that your Q49 can model? I mean, is able to model this kind of phenomena like an evaporation or solidification of some phases?
I would hope so.
Okay.
However, that's not something that we've attempted at all. Okay.
Yeah.
So that's at the moment we haven't tried anything with heat transfer, basically. So that would be, you know, a question mark in terms of how do we then move into those type of applications. I can't see why that won't work. Okay. Donzang is working a lot on Lattice Boltzmann for porous media, so he's got good experience on that. However, we're still using at this stage either low order Lattice Boltzmann, yes, or pore network model to really get fast simulations, basically, when we look at bigger porous media domains.
Yeah.
But yeah, I would think that the capabilities would be there. It's more about, you know, implementing that for a specific application that would need the thermal transfer.
Yeah. Okay. I mean, the application is huge. I mean, this is a CO2 injection, supercritical. And yeah, I mean, I've seen that pore network flow, they use it, but that's not that accurate. I mean, that's my problem with pore network modeling. And I never seen that with Lattice Boltzmann, but when you say that Q49 is a thermal, I was thinking maybe this can be done. Yeah, you're right.
Yep, and basically, like, you know, if you go back to here, yeah, basically the heat flux can be calculated here, yeah, using this third order moment. Okay.
I agree.
So the only thing is what we stopped at so far in our developments is using this pressure tensor, because we needed that to get the surface tension and diffusion and pressure. We haven't moved into that. Okay, but I can't see why that you know, yeah, there's no reason why it won't work.
Yeah. Thank you.
Great. Thank you. So other questions from the audience? Travis, you've got your hand up. Go ahead.
Yeah, I was just wondering what the main reasoning for moving to these like multi-speed lattices was. Is it for stability or is it for recovering your higher order moments here?
Can you just repeat your question?
Yeah, I was just wondering about the motivation for the higher order lattices, because if it's for stability, have you considered more advanced collision models rather than the multi-speed lattices, for example, like cumulants or cascaded LBM?
No, we haven't been through that at this stage.
Because yeah, because we've done a fair bit of work in it, and we kind of find that the stability is more enhanced from the actual collision operation itself, rather than introducing these higher order lattices, which then have like detrimental effects on your computation and on your boundary conditions.
Yes. Yep. And the other. Yeah, the other option is also to investigate macroscopic LB. So that's another direction that may be available. But initially, the idea was to really being able to retrieve the pressure tensor, and so that we needed this high order expansion, not necessarily the high order lattice structures.
Yeah, because I've also done some work on thermal LBM that's kind of related to the last question, I suppose. And you can also do dual population models. So you'd have kind of two lattice Boltzmann populations that you're resolving, and so you have one that recovers your hydrodynamics, and another that kind of recovers an energy style equation, and then you can build in phase transition into that.
So how about the computational cost and the stability of that, because we try to do this type of approach for the viscoelastic models, where we try to resolve the polymer field using a different lattice Boltzmann compared to the hydrodynamic field. But then that was quite computationally heavy.
Yeah, so for us, it is quite computationally heavy. I got a PhD student working on it at the moment, looking at two-phase, where one phase is non-Newtonian. But the stability we've resolved pretty well. We use what they call a weighted multiple relaxation time operator. Okay, so it's a standard lattice that uses your nearest neighbors, but it's just a more advanced collision kernel to recover the stability properties that we need. Yeah, it just might be something to consider if the boundary conditions and computation become an issue with the higher order lattices.
Sure. Yep, for sure. That's good points.
Good, great. Okay. Any other questions from the audience? Maya, you've still got your hand up, but I think that that's probably just an old hand. Yeah. All right, last chance. Otherwise, I think we'll finish up for today. We'll thank Emilie once more for her excellent talk, and I hope to see everyone next week for our next AFMS seminar. Thank you.